Hello everybody, welcome back. Last time we talked about standing normal shocks as well as the normal shock relations, and we had a discussion about shocks in nozzles, and then there was a moment where I said for a certain level of back pressure you would have some sorts of shocks in expansion wave structures outside of the nozzle in the external flow. And today we're going to work towards understanding those external flows, those sorts of shock and, like I said, expansion wave structures. However, before we get started, I thought we should look at a cool video since the things that we're learning about are so interesting to look at. I'm going to show you some Schlieren photography that was done by a gentleman named Destin at SmarterEveryDay is the YouTube channel. I'm sure many of you have seen his work. He's one of the sort of greatest of all time educational YouTubers out there. And yeah, so in this video, they're firing supersonic bullets past the Schlieren photography setup, so you can see Schlieren sort of allows you to visualize the density variations in air, and it's a really great way of capturing shock waves. And so in this video, the rifle is off to the right of the frame, and when it fires, you can actually see there's a pretty complicated shock structure here. So as I advance the video forward, you can see that, and I'll stop it right there. So you have that hemispherical shock wave, right? It's the big, almost vertical one, and that's actually from the weapon being discharged. Okay, so that's from the actual explosion of the weapon being fired, and then you can see these oblique shocks that are attached to the supersonic bullet off the leading and trailing edges, and so this is just pretty beautiful. You can really see how all these shock structures propagating in space, and then you can off to the right there you can see the exhaust plume of the weapon as well, and then on the bottom there are reflected shocks off of the table surface below. So the strong one that's traveling up, that's a reflection of that initial blast shock wave that the bullet is passing through at the beginning of the video. So really cool dynamics on display. I'll be sure the quality of this. Of this download here is not the best, so I'll be sure to include the link to the original video. There's a bunch of other really great bits of photography in that video, and Destin has all sorts of really good Schlieren photography in his channel. You should definitely check it out. so yeah, I mean, you can't quite see here because the resolution isn't high enough on this download that I have, but you can even see the little bits of dust in grit that were ejected through the rifle barrel, creating their own little shock fronts as they move through space. Very cool and interesting. So yeah, again, I encourage you guys to go and check that video out. But today, what we're going to learn about is moving shocks. So shocks that move, kind of like this larger blast wave from the discharge of the weapon, as well as how learning about these moving shocks can help us derive the relationships associated with these oblique shocks, which are the shocks that are attached to the leading and trailing edge of the bullet that you see in this bit here. Okay, so yeah, so that's very interesting. Like I said, go ahead and take a look at the video. But yeah, so let's go ahead and get started. We'll just get going with the first topic, which is just moving normal shocks. Okay, so in this case, we're going to imagine something like the weapon being discharged, some sort of explosive of some sort, is set off far away. So explosive set off far away. And what that looks like is, we have some sort of explosion here. We'll kind of give it some color. Okay, and then immediately after that explosion happens, there's this sort of spherical concentric shock wave that propagates outwards from that disturbance, right? And at later time steps, since this explosion is close to the surface, it might look like some sort of dome, and then it propagates outwards. And let's say that we're standing, quite far away. We'll put like a dot here to indicate that we're standing very far away. And we're standing right here, and by the time the shock reaches us, it's basically perfectly vertical and straight up and down. And so you could say that it's like a normal shock. Okay, it doesn't have any curvature to it. So we'll treat it like a normal shock. And we'll say that the shock is traveling at us at a speed of negative 548.6 meters per second. Okay, negative because we're defining the positive x direction is going to the right here. And then we know that the conditions upstream of the shock, where we're standing, are just like standard temperature and pressure. So 101.3 kilopascals, and the temperature would be 298 Kelvin. Okay, and then we also have, of course, that the velocity of the flow is 0. It's just quiescent. We're just sitting in calm atmosphere. And then the question becomes, what happens after the shock passes? What is the new pressure? What is the new temperature? And at what speed is the flow traveling after the shock passes? So we're going to, by using the things that we learned from the last lecture about normal shocks, we're going to answer these questions. So the first problem, though, is that this problem is not steady. Okay, so from our vantage point, the shock is moving. So it's covering ground. So all of our equations that we derive, like all of our conservation equations, almost everything that we've done up to this point assumes steady state operation. And so in order to make things tractable, we need to fix our reference frame to the shock. So to make things tractable, we fix our reference frame to the shock. Okay, so what does that look like? Well, now we have this set up down below. We have the shock, and the shock now is not moving, right? So Vs prime, in our new reference frame, that's what the prime indicates, Vs prime is equal to 0. Okay, and so the static pressure, after our shift in reference frame doesn't change, right? If you just measure the pressure of a bit of gas, it shouldn't change. That the pressure of that gas doesn't change whether you're observing a container of gas from across the room and you see that the pressure reading is a certain amount. The pressure shouldn't change if you suddenly start moving, right? So the static pressure is the same. It's just 101.3 kilopascals. The static temperature is also the same. It's just it's 298 Kelvin. But the velocity of that gas now, so like imagine you're observing a container of gas from across the room. If you start moving and in the negative direction, like we're moving here, that container of gas would appear from your perspective to be moving in the positive direction at whatever speed you're moving, right? So V1 now is equal to 548.6 meters per second. Okay, and then the question becomes, what is P2 prime? And T2 prime? Well, first of all, we know that, like we just mentioned, these are just going to be P2 and T2, but we still need to figure out what those are. And then, what is V2 prime? So what would V2 prime be from our new reference frame? Well, it would be whatever it was before, right? But we're going to subtract off of whatever relative boost that we're giving to it, right? So if we're moving in the negative direction, negative x direction at 548.6 meters per second, and the gas was stationary, then it would suddenly be moving in the positive direction at that velocity. But if it already was moving in the positive direction, then it's going to appear to be moving faster, right? So what you have here is just V2 minus Vs, where Vs, remember, is a negative number here. Okay, so if you're ever struggling or confused about boosting between different reference frames, just always hop on. Imagine in your head. Okay, imagine you're, say, observing a room that's far away, not necessarily air that you're immersed in. It's a little bit easier sometimes if you think about the room being far away. And then you start moving relative to that room, and you ask yourself, okay, which direction is the room moving now? And then you can then apply the requisite changes associated with things moving around within that room. Okay. Now, this problem here is steady. Now, and because this problem is steady, we can apply all of the same sort of mathematics that we applied in the previous lecture to analyze normal shocks. So the first thing we want to do is we want to find the speed of sound in the upstream or before the shock passes. So first, find A1, which is going to be the same thing as A1 prime, since it depends on just the static temperature. Which is gamma RT1, which equals, in this case, 346 meters per second. And then we can then use V1 prime to see that M1 prime, which would be equal to V1 prime over A1, is equal to 1.59. Okay, and now we have the upstream Mach number, and once you have the upstream Mach number, you can basically get everything downstream, right? As long as you are looking at a normal shock at steady state. So the normal shock relations then tell us, by going to the table and the entry for the table corresponding to M1 equals 1.59, that M2 prime, so we're working in the prime reference frame, don't forget, is 0.67. P2 prime over P1 prime is equal to 2.78, and T2 prime over T1 prime is equal to 1.38. Okay? So then we sub those into all of our values. We know that P2, which is the same as P2 prime, is equal to 2.78 times P1, which happens to be 281.9 kilopascals. We have that T2 is equal to 411.5 Kelvin. And then we can get what V2 prime is. So V2 prime is equal to M2 prime times A2, right? And A2 depends on T2. So here we're just going to have 0.67 times the square root of gamma times R times 411.5. Okay? And then what we end up with there is 273 meters per second. Okay? And what this tells us is that the original V2 is equal to V2 prime plus Vs, right? Vs is a negative value, negative 548.6. So that tells us that V2 is negative 275.6 meters per second. Okay, so after the flow, or after the shock passes, the flow is sort of following after the shock direction at 275.6 meters per second. Okay, so now a quick exercise. Question is, what are T1 and T2? Pause the video for a second and think, should these be the same? How should they change? What do you expect, right? So, first off, we know that because the flow is quiescent before the shock arrives, TT1 is just equal to T1, which is 298 Kelvin. But TT2, the stagnation temperature after the shock passes, is equal to 411.5, which would be the static temperature, times 1 plus gamma minus 1 over 2 times M2, the unprimed M2, squared. And that unprimed M2 we need to calculate using this value here that I've just outlined in red. Okay, and if we do that, what we end up with is 463.7 Kelvin. So take a minute here. When we talked about normal shocks in the last lecture, we said that stagnation temperature does not change across the shock. Okay, but here, look, they're very clearly different. So what's going on? I encourage you to pause the video and really think about this and make sure you try to come up with an answer before you proceed, because there's an important point here. So the important thing is that we are calculating these stagnation temperatures in the frame of reference that is not steady. And so because we use the 1D energy equation for steady flow to show that when you have Q and the heat and work both equal to 0, that in that case you would end up with a stagnation output that was constant. That only works for steady scenarios, but the unprimed reference frame is unsteady. So sort of what gives? The answer to that is unprimed reference frame is unsteady. HT is equal to a constant only for 1D steady flow with Q equal to WS equal to 0. Okay? So keep that in mind. Okay, so then let's go ahead and proceed to a different kind of scenario. So that is just your sort of let's say, standard traveling normal shock problem, okay, setup. So the next thing that I want to talk about are reflected shock waves. And in that video, if you go look up that video and watch it again, you can actually see some of the shock waves reflect up off the bottom of the table in some of the Schlinger photography videos that Destin shows. We'll work with a little bit more of a simplified scenario where we just have kind of what is usually termed as a shock tube. These are very common research implements. And you have the following case where you have an incident shock, which is traveling down the tube at Vs, or the shock velocity, Upstream, the flow is quiescent, it's not moving, shock hasn't arrived, and then downstream of the shock, we'll call it VD, I guess, is moving like this. Okay, it's following the shock, just like we just derived. Okay, and then, in fact, it's going to become the upstream velocity for the reflected shock. So we actually are going to call it VU. I just noticed that in the notes. That's why the label was that way. So this next sort of time snapshot that I'm drawing here is the reflected wave. So now the shock has reflected, and it's going in this direction at this velocity VR, and now you have this VU flow that it's encountering on its way back. Okay, and strictly speaking, we know that V reflected is going to be less than V shock. Okay, and we also know, just because of conservation of energy and symmetry, that the flow has to be quiescent downstream of the shock, or after the shock leaves it in the end of the channel, because where would the flow be flowing, right? Sort of forced to be V equals 0. So, like before, to be able to do this analysis, we need to fix our control volume to the shock. Okay. So now it just becomes the same sort of setup that we had before. We draw our tight-fitting control volume around it. We have state 1, state 2. And then V1 prime in our new reference frame where we're traveling with the shock. The velocity is VU plus VR, right? Because this is how the flow is moving from the perspective of a person on the shock. So the flow is normally moving in the positive direction at VU, and now you're moving towards that flow at VR, and so it adds your velocity to it. And then V2 prime is simply equal to, we'll say V2. Actually, no, we already have the labels on the second diagram. V2 prime is equal to VR, so you're leaving the quiescent flow at a velocity of VR squared, and it appears to be traveling away from you in the positive x direction at VR. P1 prime, we'll say, is equal to 2 bar. T1 prime is equal to 300 Kelvin. And then let's set VU equal to 240 meters per second. So these are all the parameters after the shock has passed through the quiescent flow on the first pass before the reflection. Okay, and then the question is, what is P2 prime, T2 prime, and VR? We want to know what the velocity of the reflected shock is. Okay, so that's what we're trying to find. So there are a couple ways to approach this, but the best way is just to start from isentropic relations. Sorry, not isentropic relations, but the normal shock relations. Isentropic is not the right term there. So we showed in the last lecture how you can calculate how properties change across the shock, simply according to the upstream Mach number, right? So we know that rho 1 over rho 2 is equal to gamma minus 1 m1 squared plus 2 over gamma plus 1 m1 squared. Okay. Also, from continuity, we know that rho 1 prime v1 prime is equal to rho 2 prime v2 prime. Since the area is constant, since dA is equal to 0, the area is not changing. So what that tells us is that v2 prime over v1 prime is equal to gamma minus 1 m1 prime squared plus 2 over gamma plus 1 m1 prime squared. Okay? We also know that a prime, or just a in general, for the upstream case, for on the one side, let's say a1, is equal to gamma RT. T is about 300 Kelvin, and so this is about 347 meters per second. Okay, that's what A1 is. Using this relationship here, that's this ratio, we can rewrite it as V2 prime minus V1 prime over V1 prime is equal to gamma minus 1 M1 prime squared plus 2 minus the quantity gamma plus 1 M1 prime squared. So essentially what we've done is just subtract 1 off of both sides here. M1 prime squared. What this gives you is, once you simplify, 2 times the quantity M1 prime squared minus 1 divided by the quantity gamma plus 1 times M1 prime squared. Okay? So if we then divide that on both sides by A1 prime, actually what we're going to do is we're going to multiply both sides by M1 prime. So if we multiply both sides by M1 prime, so I'll write that down, multiply by M1 prime, what you end up with is V2 prime minus V1 prime divided by A1, which then is equal to 2 times M1 prime squared minus 1 divided by quantity gamma plus 1 M1 prime. Okay? And now we can solve for M1 prime because we know what VU is, and V2 prime minus V1 prime is just negative VU, right? So up here, if we did V2 prime minus V1 prime, we would see that that's just going to be minus VU, which is known to start with. It's 240 meters per second. So let's go ahead and sub in the numbers here. We end up with minus 240 divided by 347 is equal to 2 M1 prime squared minus 1 times gamma plus 1 M1 prime. And we can use the quadratic formula to obtain M1 prime is equal to about 1.498. Okay. All right, so just a bunch of algebra manipulating these objects. And now that we have the upstream Mach number, we're laughing, right? Because once you have that, you basically can get all of the transitions from state 1 to 2 straight from the tables. And what I mean by that is from the tables, the normal shock tables, you can get M2 prime is equal to 0.7011. You can get that T2 prime over T1 prime is equal to 1.3202. you can get that P2 prime over P1 prime is equal to 2.458. And using our upstream values, that tells us that P2 is equal to 4.92 bar. T2 is equal to 396 Kelvin. And then T2 allows us to calculate A2, which then is 399 meters per second. And then, of course, V2 prime is equal to M2 prime, A2 prime, which is equal to 280 meters per second, which by definition is itself equal to VR. Okay, so that's a little bit of a clever construction, but hopefully if you get comfortable enough with these relations, you can come up with that setup to say get at the reflected shock velocity. Okay, so yeah, a little bit of an involved example, but not too bad. Now let's proceed to a very important section. These sorts of shocks, which we're calling oblique shocks, are very important for external flows. But what they basically are composed of is it's just basically starting with a standing normal shock, and then you're imposing a tangential velocity that itself is parallel to the shock. Okay? So start with normal shock, add tangential velocity, that is parallel to the shock. Okay, so let's draw what I've just said here. So imagine we have a normal shock here. You have V1 coming in, V2 coming out. Okay, of course, M1 is greater than 1, M2 is less than 1, and V2 is also less than V1. Okay, this is just these are facts that we have, and then we're talking about introducing a V parallel to this case. Okay, so we have our perpendicular velocity, V1 perp, and then we have our perpendicular velocity out, V2 perp, which is smaller, but we have a parallel velocity, V parallel, in the mix. And the overall velocity you can draw like this. And we'd say that this overall velocity is V1, and the overall velocity on the other side is V2. Okay, so a couple of points here. So the overall V1 and V2 are no longer normal to the shock. No longer normal to the shock. So we call it an oblique shock. Oblique shock. Okay, so now what we do is we align to V1, the incoming velocity. Now align to V1. Okay, we're always going to think of things in terms of the upstream velocity. Okay, well, we want that to be our frame of reference, so to speak. Okay, and this is what you're about to see is sort of your canonical oblique shock diagram. So we have our V1 coming in horizontally, okay? Like I said, we aligned it that way. And then we have our shock. And our shock is occurring at some angle theta. That angle is defined as your shock angle. So remember, this is the angle measured relative to the incoming flow velocity, the overall flow velocity. That's the way the shock angle is defined. Okay, we have our velocity that is parallel to the shock, so it's in this direction. And then we have a velocity that is perpendicular to the shock in that direction, right? And we call that V1 perp. And then this is V parallel. Okay? And then coming out of the shock, we get a smaller velocity, V2. Or sorry, V2 parallel. So V2 perp, I should say. The smaller perpendicular velocity, V2 perp. And then V parallel, because it's parallel to the shock, does not change across the shock. So the magnitude of these two vectors should be the same. And what you end up with is, because the magnitude of the of the parallel velocity components remains the same, but the perpendicular component shrinks because it's going through a normal shock, the overall velocity on the other side is deflected slightly. So V parallel is the same, and the overall velocity gets deflected, and that deflection angle measured relative to the incoming overall velocity direction is denoted as delta. So delta is the deflection angle. So that's the change in direction of the overall flow, okay? So how do we analyze these? Well, first off, we actually can still use just the normal shock relations. So we can still use our normal shock relations. But we just have to focus on the perpendicular velocity component. So we know that V1 perpendicular is equal to V1 sine theta. And so we can, divide both sides by the speed of sound on the upstream flow. And so what we get is M1 perpendicular is equal to M1 sine theta. Okay. And then because the shock exists, we know that M1 perp must be greater than 1. And then that just becomes our upstream Mach number that we use for the tables. Okay? So this sort of requirement of M1 perp being greater than 1, that imposes a minimum shock angle. So the minimum shock angle is M1 sine theta min is when that is equal to 1, which tells you that theta min, which itself is a function of the overall Mach number, the upstream Mach number, is equal to the inverse sine of 1 over m1, which you may actually recognize from our discussion about the Mach cone. So sine inverse of 1 over m1 is equal to sine inverse of a1 over v1, and that's equal to mu, which is the Mach angle, right? So our Mach angle is equal to theta min. Okay, and then the max angle is theta equals 90 degrees, which is just the normal shock. So we've gone from oblique to normal in that case. Okay, one thing that I wanted to note on this diagram that will be useful is this angle right here. And I do encourage you to pause for a second and look at this diagram and try to just reason about what that angle is. But just for simplicity, it's theta minus delta. Okay? So you'll find it useful to know what that angle is downstream of the shock. All right, so next is we want to find an expression for the deflection angle. So let's derive an expression for delta. And of course, as always, we start with continuity, which tells us that rho 1 v1 perp is equal to rho 2 v2 perp. Okay? We're going to express v1 perp as a function of the parallel velocity, tangent times theta. And then this is where that angle definition that I just pointed out is useful, because v2 perp is equal to v parallel times the tangent of theta minus delta. Okay? So looking up here, we're looking at opposite over adjacent. v2 perp is going to be equal to v parallel tangent of theta minus delta. And so if we then use this continuity relationship and solve for rho 2 over rho 1, we get something that just depends on the shock angle and the deflection angle. We also know from before, we've already noted this equation just earlier in this lecture, that rho 2 over rho 1 is equal to gamma plus 1 m1 squared over gamma minus 1 m1 squared plus 2. Okay? So if we set these together, if we set these equal to each other, we end up with tangent of theta over tangent of the quantity theta minus delta is equal to, of course, let's substitute in the perpendicular. We're working in the perpendicular direction, correct? So let's make sure we use the correct definition of the perpendicular Mach number. And so what we get is gamma plus 1 m1 squared sine squared theta over gamma minus 1 m1 squared sine squared theta plus 2. And we, through a bunch of complicated algebra that I'll spare you from, you end up with tangent delta is equal to twice the cotangent of theta times the quantity m1 squared sine squared theta minus 1 divided by m1 squared times the quantity gamma plus cosine 2 theta plus 2. on the denominator there. Okay, so this is a important relationship. So it's showing you that the deflection angle delta is a function of the incoming overall Mach number m1 and the shock angle. All right. So, but for a given delta, there are two possible shock angles. For a given delta, there are two possible shock angles. So, there's no explicit expression for the shock angle theta. So what we usually do is we visualize the relation in a plot. And in the back of the book, there are plots that look like what I'm going to sketch out here. So you can sort of, if you know what delta and or theta are, as well as the upstream Mach number, or if you know what delta and theta are, you can find the upstream Mach number, or if you know 2 out of the 3, you can find the upstream the other. But what we're going to plot here is theta on the vertical axis, going from 0 degrees to 90 degrees. Of course, because those are the 90 degrees is the maximum normal shock case. And then on the x-axis, we're plotting as a function of m1. Okay, and then what we're doing is we're plotting delta. So if delta is equal to 0, we get the following, where it's straight across the top. That's the normal shock. So let's say you have 0. So what we're saying here is that if you have 0 deflection angle, one of your solutions is the following, where you have delta equals 0. Okay. And then this is what you call the strong shock limit. And I'll explain what I mean by strong and weak shocks in just a second, but just bear with me. And then if you have 0 deflection, but you're at the maximum shock angle, minimum shock angle, so you're at mu, then your delta as a function of m1 looks like this. It's like this downward concave down line. And that is also 0 deflection angle, but this is the weak shock limit. So what do I mean by strong and weak? A strong shock, it results in a bigger change in properties across the shock, okay? And a weak shock results in a smaller change in properties across the shock. Normal shocks are the strongest shocks. They cause the largest change in properties because all of the flow kinetic energy is directed perpendicular to the shock. So all the flow properties, there's no tangential component of the flow velocity that's not changing across the shock. All of it is changing. So that's a strong shock. The weak shock limit is the weakest possible shock that you can form, where the perpendicular velocity is pinned right at 1. And so if the perpendicular velocity is pinned right at 1, then there cannot actually be a full-on shock forming that changes the properties. So it's the dividing line between a shock occurring and not occurring. Okay, and you can plot other lines of delta, and they end up looking like this. They're flat in the top and they curve and follow this. Okay, and then each of these, in this direction you have increasing delta. And then in this direction you have increasing delta. And then there's, if you fix a certain Mach number and you go to whatever the maximum deflection angle will be, that's what I'm plotting now, which is a dashed line that sort of runs through the center of these curves. Okay, so that's your locus of delta max. Okay, and just to remind you what that is, that's if you fix M1, find max deflection angle. Okay? So this right here is called the Mach line. And then this is right here corresponds to the normal shock condition. Okay? So let me write down some of the things that I said when I was talking about the difference between normal and weak shocks. So first off, strong shocks higher normal Mach number, leading to larger pressure drops. Larger changes in properties across the shock, hence stronger. Okay. Another fact, strong shocks always result in an overall downstream Mach number M2 being less than 1. Okay, however, almost all weak shocks have M2 greater than 1, except for those with a deflection angle really, really close to the maximum deflection angle for a given Mach number. So take a second and think about how that can happen, right? The answer to that question is to really take a look at this diagram, right? Essentially, a weak shock is a case where your perpendicular velocity is not changing very much, and your parallel velocity might be quite large. And so the downstream velocity V2 might be large enough such that M2 is actually greater than 1, even though V2 perpendicular would not result in a perpendicular Mach number downstream that's greater than 1. Okay, all of that in words, hopefully supplemented with that picture there, explains why the weak shocks have a supersonic overall Mach number downstream of the shock. Okay, so that's sort of our intro to oblique shocks, and we'll talk about those in great detail and use this analysis plenty as we go forward. But now, what I want to talk about is this idea of changing flow direction. Okay, so we talked about how that oblique shocks result in a deflection angle, right? And what I'm going to show here is that a requirement to change your flow direction with a supersonic upstream flow is what gives rise to oblique shocks. Oblique shocks occur to satisfy a flow direction boundary condition. Okay, so that's what sort of governs. That's what causes the formation of oblique shocks around objects. So oblique shocks result in change in flow direction as we saw above. So this is part of what governs the formation of oblique shocks around objects. Okay, so let's imagine that we have a wedge. It's shaped like this, and we have some sort of incoming flow that's coming in horizontally at M1. Okay, and this wedge has a half angle of delta. Okay, and essentially what the wedge wall does is it enforces a parallel flow boundary condition. So wedge enforces parallel flow boundary condition. And so M2, or the flow after it encounters the wedge, has to be parallel to the flow. So a shock forms to create the necessary deflection angle delta. Okay, and that shock that forms looks like this. Okay? So in external flows, there's almost always not a strong enough pressure gradient available to drive strong shocks. So we are going to always see weak shocks in an external flow. So no large delta P to drive strong shocks. So always see weak shocks, which corresponds to the case where M2 remains greater than 1. Okay? So the question becomes, what happens if the required deflection angle is greater than delta max, right? What happens if delta is greater than delta max? We'll just put delta required. What happens is that the shock becomes detached. Okay, so let's draw that scenario. Say we have a kind of a blunt object with a wedge out front that's with a very, very large deflection angle, required deflection angle that's greater than delta max for a certain incoming M1 flow field. Okay, and then the object just sort of continues on in this direction. So what happens is that the shock is detached, and you get it. You're required to have something like a normal shock detached from the object. So the shock looks like this. Oops, sorry. Like that. Okay? And just downstream, you get subsonic flow. Right? And now, once the flow becomes subsonic, now it can adjust its flow direction accordingly, right? Because it's no longer sort of information limited, so it can vary continuously. So directly upstream of the center of the wedge, you'll end up with a normal shock. And then, as you go off of that strongest shock condition just downstream of the center of the wedge, the required deflection angle gets smaller and smaller, okay, as you move up in this direction. Then eventually, there's this line here, which we'll call the sonic line. And then at this point, the required deflection angle is small enough to result in a weak shock. So that's why at this point the oblique shock starts to be flat and extend out. So at this point, delta R small enough to result in a weak shock. And the result of that is that everything to the right of the sonic line is supersonic. Okay. So just upstream of the object, you have this brief transition to subsonic so that the flow can properly adjust its flow direction around the blunt object. But for everything that enters sort of beyond this sonic line point, that can adjust the flow direction to be, or does it through a weak shock from that point forward. Okay, and this subsonic flow becomes supersonic again as it turns out and around this outer edge, which we'll talk about in the next lecture when we talk about expansion waves. Okay, so detached shock here. I didn't write this down. So in words, what happens is we have a detached shock. Make sure we get that down on the page here. Okay, so you can think of delta max as the maximum deflection angle for which a shock can remain attached. Shock can remain attached. Okay, so drawing it like this. So let's say we have some delta, which is less than delta max, and the flow is trying to come in this direction, and 1. This is a wall. Same with this here. This delta deflection angle is greater than delta max. So in this case, the shock is going to be attached to this corner here. And you're going to have M2. But in this case, you're going to have a detached shock. And the flow will become subsonic. Okay? And then one last note that I'll leave you guys on is that we can use this principle to measure Mach number, incoming Mach number. So imagine that you have this measurement apparatus, which is called a pitot tube. You may not have heard of this before, but essentially it's like this. So you bring in a tube that has an opening that faces the direction of the incoming flow, and then you have some sort of pressure transducer or pressure measurement device at the end, and then you have a pressure measurement device that's a tap on the side. So this is called a tap on the side, and this is called a pitot tube. So The question is what is the pitot tube measuring, right? And the answer to that is it actually measures the stagnation pressure, okay? Because the flow flowing into the tube stagnates against the pressure sensor, and so as opposed to the tap, which is perfectly perpendicular to the flow, so that one's measuring the static pressure, and the pitot tube is measuring the stagnation pressure, okay? But let's say that we have some sort of supersonic Mach number coming in. What we can do is we know that since the pitot tube is a blunt object, that a detached shock is going to form around it, right? And so what we can do is we can take PT2 over P1 and know that that's going to be equal to PT2 over PT1, and this thing is going to be some function of M1. And then we also know that PT1 over P1 is some function of M1. And then you can solve for M1, right? So that's how you could find the upstream flow velocity using this principle. In the subsonic case, you would just calculate the stagnation pressure directly because the density is constant. It's easy to calculate the stagnation pressure in that case. But you can't do that in this case because it's supersonic and you would get the incorrect value. So that's sort of one practical consideration, one way that people have made these measurements in a hypersonic wind tunnel, for example. Okay, cool. So that concludes this lecture. In the next lecture, like I alluded to, we're actually going to talk about expansion. So we talked about the types of change in direction that necessitates a shock here, a compression. And then in the next lecture, what we're going to look is the case where the flow turns around a corner into open space, necessitating some sort of drop in pressure or expansion. And that's called a Prandtl-Meyer expansion. And then once we have those two pieces, we can start looking at nozzle exits in much greater detail. So stay tuned for that. Hopefully that will be interesting. But until then, take care of yourself, and I'll see you next time.